Welcome back. In this video, we will introduce marginal and conditional distributions. So we'll start by defining a marginal distribution and what that represents in terms of variables related to their joint distributions. We'll then define conditional probability distributions. So let's start with the marginal probability distribution. So let y1 and y2 be jointly either discrete or continuous random variables. Here we actually have the definition for both, with probability function p of y1 and y2 or probability density function f of y1 and y2. Then in order to get the marginal probability function, we'll either sum or integrate, depending on our variable type, over the variable that we don't want. So for example, if we'd like to find the distribution of y1 alone, we can do that by taking the joint distribution and integrating out or summing out the variable we're not interested in, say y2. Similarly, in order to find the marginal distribution of y2, we'll integrate out y1. So we'll just integrate over the variable that we're not interested in. Please ignore the dogs barking. So let's take a look at an example with a discrete distribution. From a group of 3 Republicans, 2 Democrats, and 1 independent, we'd like to form a committee of 2 people. We'll choose this committee in the fairest way possible by random selection. So we'll let y1 denote the number of Republicans selected, y2 denote the number of Democrats selected. Let's find the joint probability function. So in order to find this joint probability function, we need to first figure out, well, how many possible member committees are there? So I've selected each member D1 for Democrat 1, D2 for Democrat 2, I for independent, R1, R2, R3. And then added up or counted how many Democrats were on the committee and how many Republicans were on the committee. So Y1 represents the number of Republicans, Y2 represents the number of Democrats. We have 15 total ways to choose this committee, 6 choose 2. I then used R to come up with a 2-way table of the assignment, and here is what we get. So for example, there are 3 different samples where Y1 is 1, so there is 1 Republican and no Democrats. Assuming then that all of these samples are equally likely, we get the following joint probability mass function. So now to get the marginal probability function, what do? Well, we find the margins. We add up across all of the values of the variable that we don't want. So for example, the marginal distribution of y1, the number of Republicans. y1 equals 0 occurs with 2/15 plus 1/15 or 3/15 probability. y1 equals 1 occurs with 3/15 plus 6/15 probability, or 9/15. y1 equals 2 occurs with 3 out of 15 probability. Same thing to get the marginal distribution of the number of Democrats. y2 will add across the columns. So there we get our marginal distribution in red. Now let's take a look at a continuous example. We'll let f of y1 and y2 represent the joint probability function. Values are 2y1, where y1 is between 0 and 1, y2 is between 0 and 1. So that's our joint distribution. What we'd like to do is find the marginal density for y1 and y2. So first, let's visualize this joint PDF. So we have y1 on the x-axis, y2 on the y-axis. The shading represents the value of the PDF, so lighter colors of blue indicate higher probability density. Now y1 overall along the x-axis looks like the density is tending to increase as y1 is increasing. For y2, the density looks fairly constant. There's not a lot of vertical change in that density plot. Now to get the marginal distributions here, we'll simply integrate out the variable that we don't care about. So let's start with the marginal of y1. To find the marginal of y1, we'll take the joint PDF, so we'll take 2y1, and we'll integrate that with respect to y2, the variable we're trying to eliminate. y2 runs from 0 to 1, so that's our integral. That gives us 2y1, y2, evaluated from 0 to 1, So the marginal distribution of y1 is 2y1. Now thinking about the bounds on y1 still ranges from 0 to 1. To find the marginal of y2, we'll integrate again, but we'll integrate out y1 for this. So our marginal of y2 is 1, or a uniform distribution. Now, in some cases, we might want to condition on a random variable instead of, say, a discrete event. So think about what we've learned previously related to conditioning. For events A and B, we know that the probability of A and B both occurring is the probability of A times the probability of B given A. Now we can certainly extend this to a discrete distribution. So the joint distribution would be the analog here of the probability of A and B. So the joint probability mass function P of y1 and y2 should be the same as P1 of y1 times the conditional distribution of y1 given y2. We can write this the opposite direction, the marginal of y2 times the conditional of y1 given y2. This also applies in the continuous case. So let's let y1 and y2 be jointly discrete, random variables with joint PMF P of y1 and y2. In order to find that conditional discrete probability function, what we'll do is take the joint probability mass function, so the joint PMF, and we'll divide that by the marginal with respect to our conditioning variable. So to get the conditional distribution of y1 given y2, we'll take the joint distribution divided by the marginal distribution of y2. Same thing in continuous space. In order to get the conditional density function of y1 given y2, we'll take the joint distribution f of y1 and y2, divide by the margin of y2. Same thing if we'd like to flip the condition. The conditional distribution of y2 given y1 is the joint distribution of y1 and y2 divided by the marginal distribution of y1. So let's take a look at an example. We have a soft drink machine that has a random amount y2 of soda syrup in supply at the beginning of a given day. It then dispenses a random amount y1 during the day. Measurements here are in gallons. If it doesn't get resupplied during the day, so y1, the amount that's dispensed, must be less than y2. So here is our joint density function. Our joint density is 1/2 for 0 less than or equal to y1, less than or equal to y2, less than or equal to 2. So we have a 2-gallon initial capacity. We'd like to find the conditional density of y1 given y2. So find the distribution of the amount that will be dispensed, conditional on how much is there when we begin. So to condition, we first need to find the marginal with respect to y2. So the marginal becomes the integral of 1/2 with respect to y1. y1 ranges from 0 to y2. So we then get our marginal distribution to be 1/2 y2. Our conditional distribution is then the joint divided by the marginal. So we get 1/2 over 1/2 y2, so 1 over y2 for our conditional distribution. So given some value of y2, this is how y1 will be distributed. We still have that bound on y1. We haven't gotten rid of it because y1 is conditional on what we're observing for y2. So y1 is allowed to range from 0 to y2 here. So now, given that we have this conditional distribution, let's find the probability that less than 1/2 gallon will be sold, given that we start with 1/3 gallons during the day. So y1 denotes the amount that's sold or dispensed from this machine. y2 denotes the starting amount. So we have our conditional distribution here. Apologies for that. It looks like there's an extra squared term that's snuck in. Remember, our conditional distribution is 1 over y2. So we get 1 over 1/2. And again, this is going to, unfortunately, it looks like, result in an error in the final answer. So I do apologize for that. What I would like you to do at home is this. Using the correct conditional distribution that we have found here, find this probability. Your answer should be 1/3. In the next video, we will talk about finding independence. I will see you then.